Hello, everyone. My name is Austin Joyce. Let me start by thanking Enrico and Guy for putting together this workshop. I think it's going to be a lot of fun. So what I'm going to tell you about today is some work we finished up recently with Daniel Bauman, Carlos Duaso Pollo, Hayden Lee, and Guy Pimentel that came out in this rather long paper about spinning correlation functions in cosmology and in de Sitter space in particular. So since we're all at a workshop called Cosmological Correlators, I imagine I don't have to sell you too hard on studying cosmological correlators. But just to put us all on the same page, let me remind you that in cosmology, the things we really measure are correlations between objects distributed throughout the universe, things like galaxies as a function of separation, or temperature, hot and cold spots in the CMB as a function of position on the sky. And what we do is we trace the evolution of these correlations through cosmic time, and from that, we infer the constituents and evolution of the universe. And so today, what I'm going to be interested in is tracing these correlations all the way back to the earliest moments and inferring something about the physics of inflation in the very early universe. So an important thing to keep in mind is that we never directly have observational access to the inflationary epoch or the inflationary spacetime itself. Instead, what we infer are correlations imprinted on this late time surface at the end of inflation, which serves as the initial conditions for the evolution of the universe subsequently. And so the fact that we never actually have access to this local space-time physics in de Sitter space, and really that we're only sensitive to these late-time correlations, sort of raises the question of whether we can understand these correlations on their own terms and sort of reconstruct them from some other physical principles without ever appealing to some local space-time evolution. And so that's what I'm going to tell you a little bit about today. And so in some sense, what we're trying to do is to put correlators on shell in a similar way to how in the scattering amplitudes or conformal bootstrap, the final answers are sort of bootstrapped from some underlying physical principles or consistency requirements without appealing to something like some Feynman diagram decomposition where things are computed and then stitched together at the end. And so in order to do something like this, a zeroth order question you have to understand is what are the consistency requirements that these objects even obey to start with? So, a big question is what are the consistency requirements that cosmological correlators have to satisfy? And related to that, how are the fundamental principles that we hold near and dear, things like unitarity, locality, and causality, how are these things encoded in the final answers or the final cosmological correlators themselves? And sort of understanding the answers to these questions may give us some hints as to sort of why these things are even there to begin with. And so one sort of abstract way of phrasing the goal is that we just want to reconstruct correlators sort of directly on this late time surface at the end of inflation without ever making any reference to sort of the bulk physics. We want to sort of see the regrowth of the bulk time evolution as a consequence of some boundary principles. Okay, so in particular, the study of spinning correlators is motivated sort of by one phenomenological and one more formal or theoretical motivation. So from the phenomenological side, let me remind you that all inflationary models have two compulsory particles in their spectrum. One is, if you like, fluctuations of the inflaton, or more formally, fluctuations of the clock telling inflation when to end. So inflation you should think of as a process of spontaneous symmetry breaking. Breaks time translation invariance spontaneously because there's sort of some clock telling inflation when to end. And fluctuations of this clock you can interpret as the Goldstone mode of this spontaneously broken symmetry. And so it's a very light degree of freedom. It's at the degree of freedom that gets imprinted in the temperature and isotropies of cosmic microwave background. And so Carlos told you a bit about how to think about that degree of freedom from a boundary point of view. It's a scalar degree of freedom. But today, the degree of freedom I want to focus on is the graviton, which is another compulsory degree of freedom in the inflationary spectrum, because inflation is telling you about the evolution of space-time itself. Space-time has to fluctuate, and so there has to be a graviton or a massless spin-2 excitation in the spectrum. And so in particular, it carries spin, so we have to understand how to think about particles with spin from a boundary point of view. From a sort of more abstract motivation is that we know from flat space physics that the interactions of massless spinning particles are extremely strongly constrained. roughly speaking, the types of interactions that we see in the standard model are really the only ones which are consistent. So for example, if you want to have a spin 1 particle interact with itself or interact with matter, really the only way to do that, if it's massless, is to have it interact through something like electricity and magnetism like interactions, or through the structure of Yang-Mills. If you want to have a massless spin 2 particle and you want it to mediate a long-range force, to lowest derivative order, it has to have the self-interactions mandated by Einstein gravity. And so there's a really rigid structure of consistent interacting massless theories in flat space. And one thing we want to understand is, how does this rigidity manifest itself in cosmological correlation functions? Okay, so let me just give you a brief outline of what I'm going to tell you. So first, I'm going to start by reminding you what the symmetries of the de Sitter spacetime are, and how these manifest themselves as identities that the final cosmological correlators have to satisfy. And then I'll give you some examples of solving these identities at 3 and 4 points, and so show you some interesting features that the final cosmological correlators have. And then I'll finish by summarizing and giving some outlook for the future. So the setting for what I'm going to tell you about today is de Sitter space. So in inflation, the de Sitter isometries are sort of weakly broken, but for simplicity, I'm going to focus on exact de Sitter space. And so the de Sitter isometries are going to get us a lot of mileage in this context. So if you remember, the things that we care about are really correlations on this final time surface at the end of inflation, sort of the future boundary of de Sitter space. And for our purposes, we can just think of inflation as a machine that generates this final state. And this final state encodes all of the correlations built up by the local space-time physics of the inflationary expansion. Okay? And in particular, all the information about the final state can be encoded in a wave functional, much as the same way we can encode information about the state in quantum mechanics in a wave function. Okay, so this wave functional is a function of late time field profiles of the fields propagating in de Sitter space. And in perturbation theory, it admits an expansion kind of like this. So it's a functional of these field fluctuations. They appear perturbatively in the exponential field fluctuations like this. And then there are these kernels that encode all the information about the statistics of these field fluctuations. And so if I want to extract something like correlators from the wave function, what I do is I just square the wave function, multiply by a bunch of fields, and then integrate exactly like we do in quantum mechanics. So in a very real sense, these wave function coefficients encode all the information about correlation functions of the fields phi. And so what we're actually going to focus on are these wave functional coefficients rather than the correlators themselves, just because they're more simply related to conformal field theory objects, right? And so I'll oftentimes use this terminology that, I want to associate to a bulk field phi, a so-called boundary operator O. But this boundary operator you should think of as the thing appearing in these wave functional coefficients. And the reason I'm going to call it a boundary operator is that the de Sitter symmetries which act in the bulk constrain the form of these wave functional coefficients. And the way they constrain them is that they demand, or they enforce, that they satisfy the same kinematic constraints that correlation functions in a conformal field theory do. And so you can interpret these things like operators in a conformal field theory. But I want to emphasize that nothing I'm going to say is relying in any way on the precise existence of some de Sitter CFT correspondence. I'm really just using kinematic facts about the fact that the de Sitter invariance of this state requires that these integral kernels have particular kinematic properties, but then we can interpret them and use CFT language just sort of for simplicity. Okay, so how do these de Sitter isometry constraints or conformal ward identities manifest themselves at the level of wave function coefficients? So many of these are somewhat familiar by now. So the de Sitter isometries include spatial translations and rotations. All that tells us is that it's useful to consider these wave functional coefficients in Fourier space, and that momentum has to be conserved. Similarly, these wave function coefficients will be rotationally invariant. And then the other de Sitter isometries have interpretation as dilations and special conformal transformations of these CFT-like correlators. And roughly speaking, those just manifest as a set of differential equations that the wave functional coefficients have to satisfy. And roughly speaking, the way that we can reconstruct bulk physics is to just solve these differential equations. And the way that we figure out or make sure that we're capturing the right bulk physics is to put some constraints on the singularities that appear in the solutions to these differential equations. Okay. And so this is what Carlos told you about at the scalar level. He explained how one way or some tools to satisfy and solve these differential equations. But something new happens when you have bulk massless fields, massless bulk fields with spin. And the thing that new that happens is that the boundary operators that you associate to them have the interpretation as conserved currents. They have the same kinematic properties as conserved currents in conformal field theories. And conserved currents satisfy additional constraints. Basically, their longitudinal pieces are constrained in a particular way. In particular, boundary conserved currents have to satisfy these so-called Ward-Takahashi identities. So in Fourier space, they take the following schematic form. So if I have a Fourier space conserved current and I dot its momentum into it, so this is sort of extracting the longitudinal part of this correlation function involving a conserved current. I don't get zero, but what I get is something fixed in terms of a lower point function without that current. And so these Ward-Takahashi identities tell me that the longitudinal parts of correlators involving conserved currents are fixed in terms of lower point functions. So there's some non-trivial set of identities relating correlators with different numbers of fields in them. Okay. And so what we have to do is we have to solve both the kinematic and Ward-Takahashi identities at the same time. So it now becomes kind of a constrained problem. Not only do we have to satisfy these dilation and SCT identities, we also have to satisfy the Ward-Takahashi identity. Okay, and so we need some sort of strategy to do this. So it turns out that satisfying the kinematic part of the constraints is actually not so difficult. We can use sort of the same technology that Carlos introduced in his talk. We can use these so-called weight shifting operators, which are a set of differential operators that transmute solutions to the conformal kinematic Ward identities into each other. And in particular, if you give me a solution to the kinematic Ward identities with some set of quantum numbers, some set of weights and spins or masses and spins, I can act with these differential operators to generate a new solution with different weights and different spins. And so using these sort of scalar seed solutions, which are not so difficult to find to the kinematic Ward identities, we can act with these spinning weight shifting operators to generate solutions that have spin, which otherwise would have been hard to find. Okay? And so then once you have these kinematically satisfactory solutions, it's not so difficult to stick them together in the right way to solve the inhomogeneous Ward-Takahashi identities. So to find something that has the right longitudinal piece to saturate the Ward-Takahashi identity. But once I've done that, I can imagine adding as much of an identically conserved correlator as I want. So I'm allowed to add to, once I have this solution, I'm allowed to add a correlator that when I dot it with its momentum, I get zero, right? And so it's sort of like a differential equation. You know, I need to find one particular solution, and then to it I can add any homogeneous solution I want. And together these things parameterize the most general space of solutions to the differential equation. Similarly here, I find one solution to the inhomogeneous Ward identity, and then I'm free to add any identically conserved piece I want. And together that parameterizes the full space of allowed correlation functions with that set of quantum numbers. And so the reason that this is a useful strategy is that it's actually quite easy to generate identically conserved correlation functions. It turns out there's an analog of the weight shifting operators that generates identically conserved objects, which is actually even simpler than these weight shifting operators. And so I won't focus very much on generating these identically conserved pieces, but that's just because it's comparatively easier than solving the inhomogeneous Ward-Takahashi identity. But you should remember there's always this freedom to add an identically conserved piece. Okay, so in order to efficiently parameterize and display correlation functions of operators with spin, it's useful to introduce some variables that manifest sort of the helicity scaling that external particles have. So it's very similar to what we do in flat space when we introduce spin or helicity variables. So if you remember in flat space, the complexified Lorentz group is two copies of SL2. So it has two types of indices, these dotted and undotted indices, and then correspondingly they're the square and angle brackets. So in some ways things are simpler in cosmological spacetimes because we're only trying to manifest the helicity transformation rules under the spatial SO3. When we complexify that, that's a single SL2. And so there's only one type of spinner. It only carries one type of index. There are still two spinners in the sense that there's a barred and unbarred spinner, which we need both of them to reconstruct a momentum. But now there's only one bracket. These two different types of spinner can be contracted with each other. And the way that we construct the spinner helicity variables is kind of the natural thing you might try to do, which is to take the spatial 3 momentum associated to an operator, build a sort of fake 4 momentum by introducing an additional 0 component, which is just the magnitude of the 3 momentum. You can arrange for this thing to be null. And so then you can just dot it into the Pauli matrices, and then it has rank 1, so you can write it as an outer product of two spinners like this. Okay? And much like in flat space, these are only defined up to a phase, and the rephasing carries the helicity information. Okay, so later on, I'll show you some explicit examples where the brackets carry the helicity information of the correlator. And one of the reasons that it's useful to go to these helicity variables, so one is it just makes the expressions much, much more manageable and shorter. But the other one is that it lets us write down only sort of the transverse part of the correlator, but still check these Ward-Takahashi identities. And the reason that that's doable is that it turns out the special conformal generator in spinner variables, which takes this form, it doesn't annihilate correlators involving conserved currents anymore, but what it does is it actually generates their longitudinal pieces. So for example, this K tilde operator acting on a correlator with a conserved current generates the longitudinal part of this correlator. And so that makes it very pragmatic or practically easy to check the Ward-Takahashi identities. So it's sort of a calculational simplification. Okay, so first let me show you how this technology allows us to sort of reproduce many results that are already in the literature. So here are some notable papers talking about things at 3 points, and here I'll show you how you can reproduce some of these results without with a sort of a minimal amount of effort. Okay, and there's already some interesting structures at 3 points involving conserved correlators. So for example, let's imagine that we're interested in the wave functional coefficient involving the stress tensor and two scalar operators, which is sort of the boundary dual of a correlator involving one graviton and two scalar fields. So in this case, the Ward-Takahashi identity takes this form. The details are not particularly important, but notice on the right-hand side, it depends on the 2-point function of some scalar operators. So famously, the 2-point function is only non-zero if the two operators have equal weights, or the bulk version of that statement would be that the two bulk fields have to have the same mass. Okay, so if it turns out that they have unequal masses, the right-hand side has to just be 0. And so that tells us that the 3-point function of the stress tensor in these two scalar operators has to be identically conserved. So in particular, it would have to be built out of this identically conserved like projector differential operator I mentioned before. But it's very easy to see that that thing would annihilate any putative correlator you might write down. So there just does not exist any object that has these quantum numbers, which is identically conserved. And so it just tells you that there can be no 3-point function involving this set of fields unless they have the same mass or have the same conformal weights. So there's something very special about this 3-point function existing. If, however, now imagine that we do have these two weights equal, or we have two scalar fields with the same mass in the bulk, then it turns out this 3-point function can exist. It turns out it can be very easily weight shifted from a scalar seed 3-point function. So there's a very simple operator that just spins up this 3-point function. It makes one of the external lines have spin 2. And automatically, it will satisfy this Ward-Takahashi identity because it has the correct quantum numbers and there's a unique possible structure. And one reason that this is an interesting example is that it turns out to leading order and slow roll, the graviton, inflaton, 3-point function is exactly de Sitter invariant, or in this language, exactly conformally invariant. And so it can be obtained in a very simple way from this TOO 3-point wave functional coefficient. Okay. Sort of the nice thing about this weight shifting procedure is that it makes building more complicated examples completely algorithmic. So for example, imagine I now care about the 3-point function with two stress tensors and a scalar operator. So the right-hand side of the Ward-Takahashi identity would involve a TO 2-point function, which is just 0 by conformal invariance or conformal kinematics. So it tells us this thing has to be identically conserved. So then you can try to build it with this conserved projector, sort of acting in a very systematic way. You see that there is a non-zero thing which is allowed, and there's sort of a unique structure, and it's very easy to build using this machinery. Okay, so then the next sort of most simple example that you might try, if you, another interesting fact is that the graviton 3-point function to leading order and slow roll is also exactly de Sitter invariant, and it's related in a simple way to the stress tensor 3-point function. It turns out that it can be built similarly using this weight shifting approach. And so one thing that this 3-point TTT example might raise, a question it might raise, is that there are multiple allowed stress tensor 3-point structures involving conserved spin-through operators. And so a natural question to ask is, how can this weight shifting procedure possibly generate these different kinematic 3-point structures? Because it sort of just takes as an input, say, a single scalar seed solution to the kinematic word identities. And the point is that there are multiple different weight shifting paths. Like, one way to think about it is that the weight shifting operators don't commute with each other. So depending upon the precise ordering of weight shiftings that I do, I can get different kinematic structures. I can get the different conserved 3-point functions by taking these multiple weight shifting paths. And so I can reproduce both of the allowed graviton or stress tensor 3-point functions using this weight shifting approach. Okay, so that's sort of a review of results that people have derived using other methods previously. But let me tell you a little bit about what happens at 4 points, because some sort of new and interesting things happen at 4 points. And so the most interesting thing is that it's no longer consistent to just get the quantum numbers of the process right. So in the previous case, we found that so long as we got the right quantum numbers and the right kinematics at 3 points, you were always able to find something that satisfied the Ward-Takahashi identities. But at 4 points, that's no longer true. And so schematically, similar to flat space, you can imagine, if you're interested in a 4-point function, you can construct a 4-point function via the exchange of an operator in various kinematic channels, things like the STU channel in flat space. And it's familiar already from the flat space S matrix that if I have massless particles, it's not consistent to only include exchange in a single channel. Generically, you have to include exchanges in multiple channels in order to be consistent. And in this case, we'll see that in order to be consistent with the Ward-Takahashi identity, or to solve it, you need to include exchanges in multiple channels. So a very simple example is if you have the 4-point function of a massless spin-1 particle with some scalar operators, it's not consistent to have only S-channel exchange. You have to also have T-channel exchange, at least. Let me show you in detail how that works. So the setting is, we're going to imagine that we have a spin-1 in the bulk coupled to some sort of matter field, and we want to ask about the dual boundary correlators. And I'm going to introduce some notation as KAB is just the sum of KA and KB, their momentum magnitudes. So it's very easy to construct the correlator of a single conserved spin-1 current with 3 scalar operators, say in the S channel, via weight shifting. It takes this form. So notice the spinor brackets here are just the things that are carrying the information about the helicity of the external spin-1 state. And then this kinematic structure is accounting for the fact that we're exchanging a particle in the S channel in the bulk. In particular, these singularities are the signatures of some bulk particle exchange. Okay. Similarly, we can write down the Ward-Takahashi identity associated to this correlator. So the longitudinal part of a correlator with a single spin-1 current and 3 scalars is fixed in terms of the 3-point function of these scalars, which takes this form, where I've chosen some particularly simple weights just for illustrative purposes. So it's pretty easy to see that if I look at the longitudinal part of this correlator, although it's not obvious from what I'm showing you here, it is not of this form. But if I add the ST and U channels all together, act with the K tilde operator, that should generate the longitudinal part. So it should generate this right-hand side of the Ward-Takahashi identity. So doing it in detail, you find something like this. These are, if you like, the contributions from ST and U. And we see that these pieces look an awful lot like the Ward-Takahashi identity, so that looks quite good. but there's this unwanted leftover additional piece, which is proportional to the sum of the couplings of the spin 1 to the operators appearing in the correlator. If you like, these are the charges of the operators appearing in the correlator. And we see the only way to make these two expressions consistent with each other is to have the total charge involved in the process add up to 0. And so we see that not only had we had to introduce multiple channels in order to satisfy the Ward-Takahashi identity, we've also had to impose charge conservation. So this is sort of the de Sitter space way you would rediscover charge conservation. You'd see that in order to be consistent with the Ward-Takahashi identity, you have to impose charge conservation. So you can run through the same exercise if you have multiple spin 1 fields, and you see that the only way to have multiple spin 1 operators interact with each other is through having some structure like Yang-Mills. You find that you have to have some Lie algebra structure. If you instead have massless spin 2 particles, you see that the massless spin 2 has to couple democratically to everything, including itself, and so you're sort of rediscovering the equivalence principle via these types of arguments. So the nice thing about this weight shifting approach is that it's totally systematic. So I've shown you some examples at 3 and 4 points where you can sort of weight shift and then combine the weight shifted objects into solutions to the Ward-Takahashi identity. But if I start to consider more spinning operators at 4 points, operators with higher spin, or certainly if I try to go to higher multiplicity, it becomes very hard. So it's completely systematic, but it becomes computationally intensive. And so you might want to find a smarter way or a simpler way of doing things. And indeed, there is such a way. So the answers, it turns out, are in many cases completely fixed by their singularities, or almost completely fixed by their singularities. And so if you know where the singularities of correlators are and how they behave in the vicinity of those singularities, you can use that information to reconstruct the answer. Okay, and Hayden will tell you more about that next week. Okay, so let me just summarize quickly. So the interesting thing, or the new thing that happens when you have correlation functions of spinning fields is that in addition to kinematic constraints, there are these constraints of current conservation that are required to be solved simultaneously. And the useful thing, or the powerful approach, is that you can use these weight shifting operators to satisfy the kinematic constraints, and we sort of build kinematically satisfactory objects into individual channels. But then the Ward-Takahashi identities require us to combine these channels in a very particular way, dialing their couplings such that we reproduce things like charge conservation and the equivalence principle. And something I didn't show you explicitly, but it is important to emphasize, is that it's not always possible to solve the Ward-Takahashi identities. So for example, if you try to have massless higher spin particles either interact with themselves or with matter fields, you find that there just is no solution to the Ward-Takahashi identity, which reproduces these famous no-go results about interaction of massless higher spin particles with matter. Okay, and then a very important thing, and I think is going to be the sort of way forward in the future, is that singularities control much of the answer. And so I think this gives another powerful approach to write down correlation functions of particles with spin. So I will stop there. And I'm looking forward to seeing you all next week and discussing more.